Okay, so that's just a combination. So basically you have two things on the left of the arrow, one thing on the right. Pretty much that's all it is. Two things on the left, one thing on the right. Now you can't have three things on the left and two things on the right. That's also a combination. That's a little bit more complicated. Generally we try to stick to the simpler examples in this class. So the middle example, sodium plus chloride. So there's two things on the left, one thing on the right. Combination. Follow me? Pretty straightforward?
Yeah.
Excellent. Decomposition. One thing on the left, two things on the right. Pretty simple, right? One thing on the left, two on the right, bada bing, done. Example they give is mercury oxide or mercury 2 oxide falls apart to give you mercury plus oxygen. One thing on the left, two things on the right. You don't even have to worry what the things are. Just look. Okay, on the left there's one thing, on the right there's two things. This must be a decomp or a decomposition reaction. It must be. Does that make sense?
Yes.
So combination and decomposition are the opposite of each other and they're pretty straightforward. Everyone in here has got it right now. I could show you a quiz, you could all get 100 on them. I know you could. Now, the hard ones are these ones. Single replacement. Now, when you're looking at a single replacement reaction, and we'll take the example that's up on the board and we'll talk about it really thoroughly. The bottom one's the best. So we have Fe, solid, plus, we'll get our copper 2 sulfate, goes to give us copper plus iron 2 sulfate. This is solid. Okay. So now, what I do for single replacement is I look at the left side of the arrow and the right side of the arrow. If on the left side of the arrow I find an element, so iron by itself, Fe, there's no charges on it, it's iron. It's a piece of iron metal, the element iron. On the right hand side I see copper. There's no charges, so it's not an ion, it's a solid piece of copper. That's an element. A single replacement reaction will always have that. It'll have an element on the left and a different element on the right. Okay? So here's an element. And here's an element. Different element on the left and on the right. Single replacement. Okay? Another way to look at it is, this iron replaces that copper. Single. One thing replaces another. Single replacement. Okay? But I think the easy way for me anyway is I look at it, I go, okay, an element on the left, an element on the right, single replacement. This one here. This one here. We have zinc right here. That's an element. Zinc solid. There's no charge there, so it's not an ion. And over here, H2. That's the element hydrogen. So we've taken zinc, replaced it with hydrogen. Single replacement. Make sense? Yeah. That's what you need to look for. That makes this question very simple. I personally believe, at least in my opinion, this is the hardest one to identify. All you got to do is remember, element on the left, different element on the right, single replacement, move on to the next one. Okay? Is that fair? All right. Double replacement. This is like a dancing equation. You're just switching partners. So you're at the club doing a dance, then they say switch partners, which I don't know if they do at clubs or not, but hey, you know, let's imagine they do. Look at the top example. We have silver 1 nitrate and sodium chloride. Watch what happens. Here, the silver is with the nitrate. Silver and the NO3 are together. They're associated with each other. Over here, the sodium and the chloride are associated with each other. Now watch the silver. It goes from being associated with the nitrate to now it's with the chlorine. So the silver has traded places, right? Everybody? Yes. You all see that, right? Yes. Mm-hmm. The sodium now was with the chlorine, but now is with the NO3. Watch the metals in these reactions. Always look at the metals. The metal ions changed anions. They changed dancing partners, if you will. Okay? So two things have changed places. That's a double replacement. Two things move. Single replacement, element on the left, different element on the right. Double replacement, the metal ions change anions. And that's it. That's a double replacement reaction. These things seem hard, but they're really, really simple. Yeah?
Can a reaction be both a single replacement and a decomp or a combination?
Yes.
Reaction?
Yes, they could. Oh wait, no, single replacement or decomp.
No. Single and combination.
No. Combination starts with two things on the left and one thing on the right. Double replacement. Oh, sorry, a single replacement will have two things on the left and two things on the right.
So basically, I'm asking, can it be two reactions?
It could be. There are certain like combinations and combustions are sometimes both. There's both combinations and combustions. So on an exam, if you put either one, I'd mark it right. Okay. Good question. All right. So that's double replacement. So we have so far combination, decomposition, single replacement, double replacement, and now combustion. Most people, and the book kind of goes this way, and it's not wrong. Most people think of combustion reactions as being an organic molecule, a carbon-containing molecule plus oxygen to give you CO2, water plus heat. That's a combustion reaction, no doubt about it. So in this class, that's a combustion reaction. But there are other kinds, like the magnesium plus oxygen. That's also combustion. You're burning the magnesium. So it's also a different kind of combustion reaction. So let's talk about this reaction real quick. Burning things in oxygen, especially carbon-based things, is combustion. Methane, CH4, that's called methane, plus oxygen gives me CO2 plus water plus energy. Well, let's not even put that down there. You all know that. These reactions get hot. So that's a combustion reaction. Now, we haven't talked about this yet, but let's talk about it now, because we're right here. That equation is not balanced. The equation is just not balanced. So we want to balance it. Let me show you how to balance these equations. Now, it's not hard, but I always follow the same procedure every time I do it, and it will always work. Balance the oxygen last. That's it, just balance the oxygen last. Balance carbon first, hydrogen second, oxygen last. It will always work. Carbon first, hydrogen second, oxygen last. It will never fail. Okay. So here we have one carbon. And over here we have one carbon, right? Over here we have 4 hydrogens. And over here we have 2 hydrogens. So we have to have 4, yes? So we put a 2 right there. Are you with me so far? Everybody? Yes. Balance the carbon first, hydrogen second. So now, we have to be careful with the oxygen. Here we have 2 oxygen, right? And here we have 2. Are you with me on that?
Yes.
Everybody?
Yes.
Everybody, this is important.
Yes.
There's 2 right here, right? And there's 2 right there for a grand total of 4 oxygen on the right. Is that true?
Yes.
So we have to have 4 on the left then, right?
Yes.
So put a 2 right there. Make sense?
Mm-hmm.
Every combustion reaction involving a carbon molecule right here follow the same rules. Yeah?
So there's that 2 on the H means there's 2 of the O's as well?
Yeah, this 2 literally means that you have H2O and H2O.
No, I meant the 2 on the H.
Yeah, there's 2 times 2 is 4, and 1 times 2 is 2. This number right here means there's 2 H2Os. So there's 2 H2Os, so there's 4 hydrogens, 2 oxygen. Right? Got it? No, that's a common mistake. Don't beat yourself up like I can see you're trying to do. So be nice to yourself. That's a common mistake. All right, very good. So now let's keep on. We got to keep trucking along here. Write this down. Big bold type in your book. Oxidation reduction reactions. Now, this is another kind of reaction. It's a little bit more complicated than what we've talked about so far. But that doesn't mean you can't do it. It's complicated, but it's not hard. Now, we all have heard the term oxidation. Some of you may have heard the term reduction. But in an oxidation reaction, there must be a reduction. Something's reduced and something else is oxidized. So for example, oxidation. Everyone knows rust, right? Everybody knows rust. Rust is the oxidation of iron. But in order to oxidize iron, something else had to reduce. Okay? So just keep that in mind. If something oxidizes, something else reduces. This is how it has to work. Okay? Alright. Write this down for me, please. An oxidation reaction provides us with energy from food. That's one thing it does. So it also powers our iPhones. It provides electrical energy in batteries, just like that. iPhones, iPads, computers, car batteries, everything. Oxidation reduction reaction. And there's the equation for the oxidation of iron. Okay? So write that down, and then when you're done writing that down, write down Leo Ger. Do it this way. Leo the lion says Ger. That's not really chemical, is it? Write that down. Leo the lion says Ger. Everybody, say it. Leo the lion says Ger. That's going to answer every oxidation reduction question I can ever possibly think to give you. Leo the lion says Ger. I've been doing chemistry for close to 25 years, and I still say that when I do these kind of questions, because I always forget. Because oxidation, reduction are very old words. They stem back to way back in the day. At one time, oxidation, O-X-I-D, so it involves oxygen. At one time, oxidation was the gain of oxygen. So if you gained oxygen, you oxidized. And that's still true. But now the definition has been polished to mean something a little bit different. Leo, L-E-O, lose electrons, oxidize. Write that down. Lose electrons, oxidize. Lose electrons, oxidize. So if you lose electrons, you are oxidized. So that's what Leo stands for. Leo the lion says Ger. Gain electrons, reduction. That's why it's confusing. Because to gain means to reduce. The word reduction means to lose. That's weird. But remember, Leo the lion says Ger. Gain electrons, reduction. So if you remember that little saying, Leo the lion says Ger, lose electrons, oxidize, gain electrons, reduction. Don't even think about what it means. Just remember that. And then you can answer these kind of questions. Because I'm going to show you, okay, on this reaction, what's being oxidized, what's being reduced. And you can tell me, just by looking at a reaction. All of you can. Once I show you, it's not hard. But you've got to take your time with it and learn it. Now this is important, because the first thing, provides us energy from food. It's also part of respiration. All kinds of processes in your body that use this. Alright, so let's see some examples. Examples always help. Alright. Copper plus oxygen gives us copper 2 oxide. Just like our Lady Liberty, Statue of Liberty in New York Harbor, she is made of copper. But she does not look like copper, she looks like green. That's because copper will readily oxidize in oxygen. Now, to make things worse, Lady Liberty is sitting in the middle of New York Harbor. Lots of ocean spray gets on Lady Liberty every day. So she will oxidize even faster, because salt water will help to promote that. Plus, it's foggy in New York Harbor a lot, so the water also helps promote this reaction. So Lady Liberty, even though she's made of copper, still appears to be green. So here we have copper plus oxygen will give us copper 2 oxide. And copper 2 oxide is green. Nice pretty color. So now, we can balance it. Let's just throw up the balancing numbers here. Now in this class, when you're learning about oxidation and reduction, all I really want you to be able to do is tell me what's being oxidized and what's being reduced. If this was general chemistry 2, we'd go in a little more detail. I'd tell me how many electrons are moving from one place to another. But that's general 2. This is allied health chemistry. So we're not going to bother with that. It's enough for me to know that you can identify oxidized species and reduced species. Okay, so right here, let's just examine copper. So here we have copper, and here we have copper. We're only going to look at the copper. We're going to ignore the oxygen for now. So, on the left-hand side, this is copper metal, right? Lady Liberty is made of copper metal, right? Copper metal is an element on the periodic table. Element number 29, right? What's the charge of an element?
Neutral.
Neutral, she said, with the confidence of an army. It's neutral, absolutely right. It's neutral, has no charge at all. So you could, if you want, write a little 0 right there. Tells me there's no charge. That's also a way to abbreviate metal. This is copper 0, so it's copper metal, the element copper. The orange metal sitting in front of you. Okay? Everyone like that? The copper here is involved in a compound, CuO. What's the charge on copper in CuO?
Negative, positive.
Positive 2. Good. That's very fast and very good. She's right. It's positive 2. Why is it positive 2?
Because oxygen is negative 2.
Oxygen has to be negative 2 because it's on the periodic table and it's in group 16. So it has to be negative 2. Is that correct?
Yes.
Formulas have to equal 0. So the copper must have been plus 2. Is that good?
Yes.
Everybody like that? So on the left-hand side we have copper 0, and that goes to give us copper plus 2. Okay? That's just what happened to the copper. I'm not worried about the oxygen right now. We'll worry about it in a hot second. But let's just think about the copper right now. So now, here we have copper. Here we have copper. You can be copper. These are your electrons. So these 2 blue markers are electrons. She's copper. So on the left-hand side, you're neutral. You have all the electrons and all the protons. So you have 29 protons, 29 electrons, right? Now you're going to become copper plus 2. How does she become copper plus 2? She gets rid of what? 2 what? She gets rid of 2 electrons. She gives them, say to me. Thank you. So now she's copper plus 2. Right? Does everyone follow this part though? So the metal, to become positive, must have lost 2 electrons. Right? She dished them off somehow. Right? Everybody? Yes. Leo the lion says grr. Lose electrons, oxidized. Right? She handed me 2 electrons. She lost 2 electrons. Lose electrons, oxidized. The copper, oxidized. Does that make sense? Yes. Because it lost 2 electrons, it oxidized. Is that good?
Yes.
So this copper must have oxidized. So just write OXID period beside it. The copper oxidized. Is that clear? Everybody?
Yes. Yes.
I hope. Okay. Over here we have O2. To give us, over here is O minus 2. Now, don't worry that it's not balanced with the oxygens. Don't worry about that. I'm not worried about balancing here. I'm worried about electrons. So we have oxygen. Oxygen from the periodic table is neutral, yes?
Yes.
No charge on the oxygen. When it becomes minus 2 on the right-hand side. You with me?
Yes.
So the oxygen went from neutral to negative 2. Right?
Yes.
So what happened to the oxygen? GER. Gain electrons reduction. Right? Something got reduced, something got oxidized. Right? So this is RED. Reduction. So the oxygen reduced. So when you're out on a Sunday drive in the middle of nowhere in Florida, you see a rust bucket car in a field somewhere, rust is falling off of it, you can tell your passenger the iron on that car is rusted. That means the oxygen must have reduced. Really flip them out. Using big words and stuff, right? The iron oxidized. the oxygen must have reduced. Right? Now remember that, because these questions get easy. If you can identify the oxidation, the other one is automatically reduction. It has to be. If it's not, you've done something tragically wrong. Okay? Now remember that. If I reduce something, something else oxidizes. If I oxidize something, something else reduces. They go hand in hand. With me? Does that make sense? All right. Let's do a couple more examples.
I have a question.
Go for it.
Leo and Garrett will often always decay apart?
No, not always, no. Here's an example where it doesn't. Oops. Go back. This is what I want right here. Yes, this is what I want. Now, in the lab, we did the following reaction. What's that? Oh. We have copper, I'm sorry, we have zinc. Zinc metal plus copper sulfate. Copper 2 sulfate will give us copper plus zinc sulfate. Okay, first question I have for you from here, this is a metal. So we have zinc metal going to copper metal. What kind of reaction is that? Single replacement, very nice. It's a single replacement reaction. Okay, let's look at the zinc and just the zinc. On the left-hand side, the zinc is what charge? Neutral. It's on the periodic table. It's just an element, the element zinc. So it's neutral. Very nice. And it goes, and sulfate, for those of you who may not remember, is -2. Sulfate, the polyatomic ion, is -2. So what's the charge on zinc on the right-hand side? +2, right? Everybody?
Yes.
Everyone good? So zinc becomes +2. Now copper here is what charge? +2? Everybody?
Yes.
The copper right here is +2, right?
Yes.
All right. Cu plus 2 going to give us, now here it becomes what charge? Neutral. Okay. There you go. So then copper is neutral on the right, because it's an element standing by itself. There's no charge here, so it's 0. The charge is 0. Now, there's our two little reactions. Zinc goes from being neutral to +2. Copper goes from being +2 to neutral. Okay. Zinc started out with, how many electrons does it have? Zinc has, where are we now? 30. So zinc is here. Zinc has 30 protons and 30 electrons. It became +2. So it had to lose 2 electrons, right? It had to donate them somewhere, right? So Leo the lion says, Gur, lose electrons, oxidize. Right? So the zinc oxidized. Are you good with that? Yes. So that means what for the copper? It must have reduced. Okay? Now, let's check ourselves. Copper went from +2 to 0. So wait now, it had a charge, now it has no charge. So it must have what electrons? Must have grabbed a few, right? Must have got some, grabbed them. So the Gur gained electrons reduction. With me?
Yeah.
Does that make sense?
Yeah.
Did you figure that out on your own? Let's have a look. Alright, so this one here will be oxidized. And that one there will be reduced. Okay? Now I like this slide. You don't have to draw it, but just kind of follow along with me. When you do this reaction, you literally throw in a piece of zinc metal, like a solid chunk of zinc, you just toss it into a copper sulfate solution. And what happens is the copper ions will actually smack into the zinc metal. They'll just run into it, you know. And when they do that, the zinc metal says, hey, I got 2 electrons for you. Here you go. Gives it to them. And the copper's like, thank you, and takes the 2 electrons. When copper +2, the ion, is very soluble in water. When copper becomes copper metal, we all know that copper is not soluble in water, right? We should know that because our pipes usually are made from it to bring water to our house. If it was soluble in water, that would be very bad news. Then the copper will precipitate, become a solid chunk at the bottom of the test tube. So for those of you who may not remember in that experiment we had that yellowish, orangish, reddish crack at the bottom of the test tube? That was copper.
Oh no.
Pretty neat, huh? That was an oxidation reduction reaction. All right, oops. Let me see, these are too easy. That's too hard. Well, I'll try these ones, I guess. Oops, answer's already there. So the top one, we have tin. These are this half reaction. We have tin metal. Tin on the left-hand side becomes tin 4 on the right-hand side. So the tin has what? Has it gained or lost electrons to go from 0 to plus 4? Lost. It's given up 4. So Leo the lion says Gur. So is tin being reduced or oxidized in that equation? Everybody. The middle one. This is a little tougher now. Now we got 2 charged species. Now what do? Holy smokes. We have iron plus 3 and iron plus 2. So iron 3 is going to iron 2. So to go from plus 3 to plus 2, I must have what? Gained or lost an electron? Gained. You have to gain, right? To go from plus 3 to plus 2, you gain 1 negative. You gain an electron. So gain electrons, reduction, right? Gain electron reduction. Bottom one, chlorine goes to chlorine -1. So chlorine is neutral. On the right-hand side, it's -1. So if you go from being 0 to -1, you gained or lost an electron? Gained. So you're reduced. Pretty good, right? All right. It's hard, but you guys can figure it out. Let's do this one together. This one's a little bit tough. Not that bad, but I wanted to show it to you. In your textbook, there's numerous questions on this. Please make sure you can do it, because it's going to be on your exam. Probably worth 5 or 10 points. All right. This one is not that bad. It just seems bad when you look at it. So here we have silver plus chloride, actually, giving us silver and chlorine. All right. So silver plus chloride, Ag plus 1 plus Cl minus 1 gives us silver plus Cl2. You can balance that if you want, but to do these kind of equations is not necessary. Now, which reactant is oxidized, which reactant is reduced? Basically the same kind of question I asked in the exam. So, we have silver plus 1 and silver. So silver plus 1 goes to give us silver with no charge. Is that correct? We have chlorine minus 1, Cl -1, going to give us Cl2. You can balance it if you want, but you don't have to. So we have a negative going to a neutral. So the top one, positive 1, goes to 0. So what happened there? It gained. And it reduced. GER, gain electrons reduction. Right? So this one reduced. The bottom one, you're negative going to neutral. So if you had -1 charge and you became a neutral, what happened to you?
You lose?
Do you lose or do you gain? To go from -1 to 0, do you lose an electron or gain an electron?
You lose.
You lose one, because electrons are negative, right?
Yes.
So you lose an electron, so this must be oxidation. Okay? That's how you do those. Now, they are as easy as they look once you practice. So go and do the problems this weekend, make sure you practice them up, and you'll get the hang of it, and you'll become an old pro in no time, because they're really not hard. And the question on the exam is not going to be a trick question. It's going to be pretty straightforward. So just make sure you can do it, please. All right. Mole relationships in chemical equations. Please write that down. So we spent some time last week figuring out how to convert grams to moles. Moles to atoms. We learned about the molehill, all that kind of stuff. We never really said too much what we're going to do with it. And now is the time we're going to learn what we're going to do with it. Mole relationships in chemical equations. Now, write this down for me. The law of conservation of mass. Basically, conservation of mass means the matter cannot ever be created, nor can it be destroyed. There is no change in the mass. So from the start to the finish, there's no change in mass. The mass of the products must equal the mass of the reactant. That's the law of conservation of mass. It has to be that way. You're not going to lose anything. As long as you isolate all the products, you will get the same mass of starting materials as you do products, as long as you isolate them all. Sometimes you don't, but if you did, you would have the same mass. Okay? Well, that's the first thing, law of conservation of mass. All good? Everybody got it?
Yep.
Alright. Alright, so now, consider the following equation. We have 2Fe plus 3 sulfur plus gives us 1 Fe2S3. I'm going to write that down. So 2Fe plus, oh man, 3 sulfur. Holy crap. 3 sulfur is going to give me Fe2S3. Okay? So let's consider that reaction for a minute. We have 2 irons plus 3 sulfur gives me 1 iron 3 sulfide. Well, what that means is, in this reaction, I have to have 2 atoms of iron. I must. I have to have 2 atoms of iron. I also must have 3 atoms of sulfur. Okay? That's what it's saying. You with me so far? So I have 2 iron, 3 sulfur atoms come together. Some magic happens, and I get 1 molecule of iron 3 sulfide. Okay, that's what that equation is telling us. Okay? It may not seem that way, but that's what it's saying. 2 atoms of iron, so 2 atoms here. And 3 atoms gives me 1 molecule. So far, so good? So now, what if we had 2 multiplied by 6.02 times 10 to the 23 atoms? 3 times 6.02 times 10 to the 23 atoms? To give us 1 times 6.02 times 10 to the 23 molecules. What if we had that? What if we just added more atoms up to this exact number? Not exact, excuse me, that number there. What if we just dumped in more atoms? Okay? What is this also known as? Avogadro's number, which is also equal to what? 1 mole. Right? Avogadro's number, 6.02 times 23, is 1 mole. Right? So this is also saying 2 moles of iron, 3 moles sulfur gives me 1 mole of a molecule. Oops. I'm going to put atoms here, I guess. Yeah. 2 moles of atoms, 3 moles of atoms, 1 mole of molecule. Okay? So that's what that equation means. Now you can speak in terms of atoms. We normally don't because atoms are just, one atom is not any kind of material to speak about. But a mole is a lot. Okay? So we generally speak in terms of moles. So if I were to read that equation to you, I would say 2 moles of iron plus 3 moles of sulfur gives me 1 mole of iron 3 sulfide. Okay? That's just what it means. So now, just looking at that equation, you guys could all go out and do it. How? Well, first of all, you say, okay, I need 2 moles of iron. 2 moles of iron, no problem. Go to the balance room, realize very quickly the balances are not calibrated in moles. They're calibrated in grams. No, now what do? Periodic table. You switch it over to grams. We look at the periodic table. Iron. We know that in 1 mole of iron, there's 55.845 grams of iron. Yeah? And we need 2 of them. Multiply by 2. So you need like 110 or so, right? Yeah, about 112 almost. Okay? So 112 grams of iron go into that reaction. Are you with me? You need 3 moles of sulfur. Well, sulfur is 32.1 grams. Multiply by 3. Dump in about 96. 96 grams of sulfur. Just dump it in there. Grind it around somehow. Mix it up. I'm not even sure how they do that part. But in the end, you will get 1 mole of that. You should have. If all goes well. Normally things don't all go well though. What's up?
What if they don't give you the grams? So just tell you to find it.
Pardon me? One more time.
What if your answer just find the mole?
Oh, we'll get into questions like that in a minute.
Okay.
I'm just trying to tell you what this equation means and how you can work with it.
Okay.
But we'll get there, don't worry. And when we get there, you wish we had it. No, I'm just joking. They're not that hard, they're just stepping. Alright, so that's what that means, and that's how you can do the reaction if you want it to. Alright. Oops. Here we go. I don't want to do this. You guys have already done this stuff enough. Alright. Let's do this question together. How many moles of iron are needed to react with 12 moles of oxygen? Now, these questions are not that hard. So you're probably tempted to jump to an answer. My advice is don't jump to answers. Always work the problem. That way you'll never be wrong. A lot of times when students will take, okay, here's the question, I immediately jump to an answer, you jump to the wrong answer. Don't do that. Work a question logically. Okay, so let's look at this equation here together. And it's O2, okay. 3O2, 2, O3. And we have 4 here, okay. 4. Alright, so we have that equation. 4 iron plus 3 oxygen gives me 2 molecules of iron 3 oxide. So now, the question says I have 12 moles of oxygen. So 12 moles, I just write it right here. That way I keep track of it. 12 moles of oxygen. How many moles of iron? So I'll put a question mark right here. So now from that question I know that I want to go from moles of oxygen to moles of iron. That's what the question's asking me. So then I'm like, well, let's take a look at the question. Let's just examine it real closely. So in this particular equation, I know that if I have 4 moles of iron, I must have 3 moles of O2. This number and that number are here and here. I got them right from there. Okay? Just read the equation. So to do this reaction, if I have 4 moles of iron, I must have 3 moles of oxygen. So you can just write it just like that. 4 moles of iron equals 3 moles of oxygen. That's an equality. Right? Which can be converted into a conversion factor. Right? Everybody? So then, right here, if I have moles of O2 multiplied by something to give me moles of iron. That's what I want to do, right? I want to convert moles of oxygen to moles of iron. Everybody with me?
Yes.
That's the basic question. Now, to do this, I have to put moles of O2 on the bottom. And moles of iron. Moles of iron on the top. That way my units will cancel. This is just like what we've already done through most of this class, right? Have this, need that, multiplied by something. What you don't want on the bottom, what you do want on the top, make sure they cancel, and go. So the moles of O2 cancel out nicely. So then here, I will put 12.0, because that's what I'm starting with. Moles of O2. And then I look over here. I say, okay, 4 moles of Fe, 3 moles O2. So this goes here. 3 moles O2. Does that make sense? Just like every other conversion we've done, right? Everybody? Can you see how it's the same? One person. Anyone else?
Yes.
2 people. Anybody else?
Yeah.
A few more people. And the 4 goes right here. Now, the reason why I harp on using the units from the very beginning of this class, and I say use the units, use the units, use the units, because I do questions like this were coming, where they start to look a little tougher, but they only look tough. They're not. They're the same as what we've already done. But if you haven't been using your units like I asked you to do, these questions become almost impossible. So make sure you start using units if you haven't already. So then, to convert 12 moles of O2, you simply divide by 3, multiply by 4. And that'll tell you how many moles of iron that you need. Okay? So divide 12 by 3 is? 12 divided by 3 is?
4.
4. Multiplied by 4 is?
16.
16. This and that are exact. So, whenever these numbers in the equation, 4, 3, and the 2, those are exact numbers. So you don't round to them. Okay? Does that make a little bit of sense, how to do that? Okay? Now, whatever you do, do not jump to an answer. Always kind of go through this. Once you get good at it, you can go fast, but make sure you go through the exercise because the most common mistake here would be people put the 3 here and the 4 there, and that changes the entire answer. Okay, so just go through it slowly. And let's see, there's another problem here for you guys. We'll do these ones. These ones are a little tougher. So let me get to a problem here. There we go. We'll do this one together. Now, I'm not going to lie to you. These questions get hard. And this is about as hard as they get. Okay? It won't be any tougher than this. How many grams of O2 are needed to produce 45.8 grams of iron 3 oxide with the following reaction? So now, I'm going to give you a method. Some of you will choose to adopt it and will do well. Some of you will choose not to adopt it and probably will do very bad. I'm not saying that to be mean to anyone. I'm saying that from my experience, this is what happens. If you don't go home tonight, and I mean tonight, not tomorrow, tonight, and work some of these problems out on your own and get used to the steps that you have to go through to solve these problems, and you wait till the final, or to the exam number 3, or worse, the final, I can already promise you you're going to do very badly on the exam. So don't let that be you. My experience tells me that it'll be about 30% of you that will just won't bother. If you bothered, I promise you, if you actually tried, you will succeed. These questions are not hard. They just appear to be hard. And yes, there's a lot of steps. And yes, I will hear moaning and groaning. And yes, you will still learn it. And yes, you can do it. All right, so the reaction equation is the same. Now, what I would do, well, the first thing I would do is I'm going to set up a table. Tables are nice. Why? Because tables help you keep track of all of the information. The most common mistake in these questions is losing track of where you are, or not knowing where to go. And I'll show you how the table can tell you all of that. So what you want to do is MM, grams, mole. MM, molecular mass. G is for grams. Well, you already know. G is grams, and that's moles. Okay? So molecular mass, grams, moles. That's the first thing I would do, is set this table up. So I have my table ready to go. I look at the question, I say, how many grams of O2? So I immediately go to the board, and I say, grams of O2 is the question mark. So I don't, and then put the unit beside it to remind yourself what you're doing. Grams of O2, I have no idea. No concept. Are needed to produce 45.8 grams of iron 3 oxide. So I know I have 45.8 grams of this. That appears to be all I know. But you guys are clever. And you know that you have more information. It's on the back of your exam. You have a periodic table. Right? The key to all of these questions is remembering moles. These two blanks right here are the single most important things to figure out. If you figure those out, the rest of the question is gravy. It's really simple. Okay? But you've got to go to moles. All right? You cannot ever convert grams to grams. Ever. Why? Iron 3 oxide weighs a lot more than oxygen does. Oxygen weighs 16, iron 3 oxide probably weighs close to 150 grams per mole. So you have to convert everybody to moles. Okay? A big hint. If you just don't know what you're doing on a question like this on the exam, take the grams that you're given and convert them to moles. You'll get 3 out of 10. Just for converting to moles. Okay? You follow me? That's how important converting to moles is. If you try to go from grams to grams, you'll get it wrong. I'll give you 1. Just for showing up. Okay? So don't do that. Go from moles to moles. So we need to get moles here. We need moles of Fe2O3. Why? Because if we get the moles of this, we can use this. This 3 moles of oxygen equals 2 moles of iron 3 oxide. We could use that ratio to figure out moles down here. Right? Does that make sense?
Yes.
Everybody?
Yes.
Is the idea there?
Yes.
You people.
Yes.
Few people don't have a clue yet. But we'll go get you there, I promise. Alright, so let's go back one step. What do these numbers mean? They're what? Everybody yell it. Moles. Moles. Louder. Moles. These numbers are moles. 4 moles iron, 3 moles oxygen, 2 moles of that. Right? This number is what? Grams. Is that number the same as that number in terms of units? No. Moles, grams. Okay? So you can't convert this to that because these are moles. Right? You can't convert moles, grams to grams using moles. You have to convert to moles first. Make sense yet?
Yes.
You must convert to moles. Have I told you that yet?
Yes.
That you must convert to moles. Everyone say it out loud. I will convert to moles. No matter what else I do. Okay. So I think I've convinced you that moles is important. I hope. Now there's a reason why I'm making a fool of myself doing this, because you're all going to forget. Go home tonight, right after class, and work these problems out. Like the one I'm doing right now, do it on your own. Cover up my answer. Cover up the book's answer. Work it on your own. Get it wrong. Get frustrated. Get mad. Call me names when I'm not there. That's all good. Learn it. And once you've mastered it, these questions are dead easy. They're just time consuming. Okay? Alright. So I need to convert to moles. I have grams. I'm screwed. Am I? How am I not screwed? Aha! You'll always have a periodic table. At home, it's in your textbook, front cover. On exams, it's on the back. So I go to the periodic table, I say iron is 58 point, I'm just going to say it's 58.8. I have no idea what the book says, but I'm going to call it 58.8. So I know that iron, this is right here, 58.8, oops, grams per, oh look at that, moles. Hey, look at that, grams and moles. I can convert grams to moles using something like this. Oxygen is 16.0 grams per mole. Is that true?
55.8.
Is it? Oh, I'm sorry. Oh, yeah, thank you. -1. 9 out of 10. Oh well. 55.8. Now, I have two common error. I just thought of this. It's a very common error. For some reason, and I don't really know why, people like to say, well, there's a 2 here, so that means I have 4 here. I need to do, no. Don't do that. Take just the formula I give you and don't worry about this number here yet. Okay? You're going to calculate the molecular mass of a formula. Okay? Don't worry about the balanced equation. Just look at the formula. Okay? So it's going to be 2 times iron and 3 times oxygen. Some people are tempted to say it's 4 because 2 times 2 is 4. Don't do that. Okay? It's just look at the formula, ignore that coefficient number right there. Just ignore it for now. We're going to use it later, but for now, ignore it. So 2 times Fe is 2 times 55.8 grams over moles. And 3 times 16.0 grams over moles for a grand total of, anybody? Anyone have it? I grab my calculator, no one else has one. I'll just grab it anyway. There's always a fight. You're laughing because it's true. Okay, here we go. What you get? 159.6. Everyone else get the same thing? All right, we'll rule by committee then. 159.6 is good enough for me. So that's the molecular mass of this. So write it down. Just write it right in your table. So we had a lot more information than we thought, right? We have the formula, so we have the molecular masses. We just have to figure them out. You with me on that? Everyone remembers how to do that, right? The molecular mass? Okay. So we need to get to moles. Now we have grams, and we have grams per mole. So we can easily convert grams to moles. Everybody like that? Is everyone on board with that? We did this last week, right? Converted grams to moles? Okay. I'm going to pop up the screen real quick so we can have a nice big workspace so we don't have to erase. Okay. So, we know this, put it there. We know we don't have that yet, so let's figure that out. 45.8 grams of iron 3 oxide, and we know the molecular mass. So let's run over here and figure that out. We have grams of Fe2O3. We want to multiply that by something that will give me moles of Fe2O3. Okay? We just want to convert grams to moles. No problem. We put the grams, Fe2O3, on the bottom, and the moles, Fe2O3 on the top. We did this last week, right? Mm-hmm. Everyone's at least somewhat okay with this? Yeah. So the grams will cancel out. So far, so good?
Yes.
Let's plug in some numbers now. 45.8 goes right here. The number 1 goes here. And 159.6 goes here. Goes there. I got that number from right here. That's the molecular mass. So I'm converting grams to moles using molecular mass. Get it? No? Okay. 45.8 divided by 159.6. 0.2869, so let's go 0.287. Yep, 0.287. Equals 0.287. And I put a box around these things. On an exam, the last thing you want to do is hunt for something. So if you're not one of those people, which I am not, I'm not really that neat. Numbers that I know are important are going to come back again. I put boxes around. That way I don't lose track of them. Also, I'm going to stick it in my table. That way I have it in 2 spots. So when I'm looking for it, it'll be readily available. 0.287. So in this reaction, I have 0.287 moles of iron-free oxide. Okay, so now I need to go from here to there. I need to convert that to that somehow. Okay? I look at the balanced equation, and it says 3 moles of oxygen is 2 moles of iron-free oxide. Right? So you look at the balanced equation. I want to go from iron-free to oxygen. So write that down neatly on your paper. I know from balanced equation. No, I'm just going to write the whole thing down, just so we can have it nice and clean. Just going to write the whole equation down. You don't have to be this specific on an exam, but I want to make sure everyone's clear on this. So from this, what is it? 4Fe plus 3O2 gives me 2Fe2O3. From this equation, I know that 3 moles of O2 equals 2 moles of Fe2O3. Put a big old square around that. That's extremely important. From this equation, I know this. Okay? And I will always give you the equation. I may not balance it. You may have to balance it for yourself, but I'll always give you the equation.
So 4Fe wouldn't count.
We're not even dealing with the iron. If the question had said, give me the grams of iron and oxygen, then you have to do this twice. Okay? But we're just dealing with oxygen, so we're going to ignore iron. So it's a great question. Okay, so I know the moles of oxygen, and I know the moles of iron. It's a 3-to-2 ratio. Okay. I have moles of iron 3 oxide. I have this, but I need this. Right? Everybody with me? Yeah. Okay. So, I have moles of Fe2O3 multiplied by something to give me moles. Fe2O3. The moles on the bottom. Wrong moles. O2. Moles Fe2O3 moles of O2. That's my setup. I'm going to convert moles to moles. I converted grams to moles. I'm going to convert moles of one thing to moles of another. And I use this ratio right here. It's going to be 2 down here and 3 up there. Okay? You got that from here. So right here. That is right there. Okay? You get that from the balanced equation. Yep, this is a lot. We're not done yet. Yeah, it might be. I don't know yet. I gotta get there. Okay, so we know the moles of iron. Iron-3 oxide, excuse me. It's 0.287. 0.287. This is my conversion factor, and that will leave me in the unit I need. So you take 0.287 multiplied by 3 divided by 2. Come on. 0.287 divided by 2 multiplied by 3 0.431, right? 0.431 moles. Highlight it so you don't forget it. 0.431 moles. And then you breathe a sigh of relief because you think you're done. But then you look at your table, which is why we keep coming back to it, and you say, crap. He wants grams. Urgh. Not quite done yet. In order to convert moles to grams, we need to know this, don't we? We need the molecular mass of oxygen, right? Everybody?
Yes.
We're right there. One more step and we're done. We need to know the molecular weight of oxygen. Oxygen is O2. So let's just do it right here real quick. Oxygen is O2. Oxygen equals 16.0 grams per mole. So O2 is going to be 32.0 grams per mole. Right?
Yep.
So 16 times 2, right? It's 32. So write that right in here. .0 grams per mole is my molecular weight of oxygen. So now, with all of this data, the molecular mass and the moles, this is within reach now. We can get that. So we have moles of O2 multiplied by something to give me grams O2. Moles O2 go on the bottom. Grams of O2 go on top. The moles will nicely cancel out. And this is going to be 32 up here. And 1 mole down there. And 0.431 will go there. So simply multiply and you're done. Please, for my sake, put a box around your final answer just so I can see it quick. If I have to dig for it, I'm half likely not to see it. And that's a bad thing. 13.8 grams. Even stick it in your table if you want to. 13.8 grams of O2. That's how it's done. Yes, that is a lot. And yes, you can do it. It's not that hard once you get into it. But I promise you, if you don't try it at home and you wait to the exam thinking I'm not going to put it on there, you're desperately seeking for you're grasping at straws, because I am going to put it on there. It's going to be on your exam. Not this question, but one just like it. So make sure you can do it. It's 10 points out of 100. 10%. Make sure you can do it. It's really not hard. But if you don't practice it, it's impossible. All right, for now, let's take 10 minutes. Come back. Make sure you go and do the ones that are at least online, because the answer and the solution is right there in front of you. Make sure you can do those questions without looking at the solution manual. Okay? If you can, you're good. So don't sweat it. If you can't, come to my office hours on Monday or Tuesday, or the LRC has tutors for free. You guys can go get tutoring for free from the LRC. So take advantage of something. Just make sure you can do them. They're not hard. You really just have to practice. Okay? And I don't want to see anyone do poorly on the exam because they didn't practice that question, because it's going to beat it. All right? All right, now just to lighten up a little bit, no more math at the end of this chapter, which we're almost there. Energy in chemical reactions. Now, energy basically in chemistry, we usually refer to heat. It can be light, it can also be sound, but in general it's heat. And we know this because we all burn gasoline in our cars, and we all know our engine gets hot. So when you burn gasoline, the combustion burns the gasoline, gives off energy. And we talked about, have we talked about exothermic yet? No. Today's the day. All right, so energy chemical reaction. So here, you can see basically something that is floating in a fireball. So that reaction is giving off tremendous amounts of heat. It's a fireball, right? There should be heat, right? But there's also light. And you can bet that made a noise. It probably went, and it probably scared the crap out of whoever did it. Well, unless they expected it. Okay? So energy. Now, in order to have a chemical reaction, molecules must do a few things. They must first of all, hit each other. That's number one. Hit. Smack into each other. That's the first thing they have to do. They have to actually hit each other. Collide. Collision. It's not enough to hit, though. They have to hit in the right way, in the right orientation. You can bump into somebody walking down the street, say, bump into them, oh, excuse me. No reaction, you go on your way. Bump into the wrong person, the wrong way, and it's going to be throwdown time. Okay? Energy. You must not only hit them in the right way, you must hit them hard enough. So you're walking down the street, some big burly dude's in front of you. You bump into him, but you don't hit him very hard. He might just laugh at you and say, oh, no harm, no foul. You hit him maybe in the square of the back. You might not like that very much, but he still may not react. He said, hey, watch where you're going. You hit him hard enough in the small of the back that he knows it's intentional, he's going to hit you. He's going to react to you. See what I'm saying? Molecules the same way. You have to hit in the right way, and hit with enough force to make the reaction go. All chemical reactions follow the same protocol. Now, this is going to come up a little bit later, but let's talk about it now because we're talking about hitting each other. Let's imagine every one of us in this room left. We're not going to because this takes too much time. But let's imagine we all got up and we went outside. And we took me, for example, and blindfolded me and threw me back in the room. I fall down the stairs, but I survive. Now, we'll take somebody else. This gentleman here. We'll blindfold him too. Now I won't say anything, and he won't say anything, and I'll say, find each other in this room. Imagine this room is the reaction class. Imagine we are the reactants. It's going to take us a long time to find one another, isn't it? If we ever find one another. So we may be the most reactive things in the world, but if we can't find one another, we're not going to react. Right? Now, let's imagine we do find one another. We have to hit in the right way. So the odds of us finding each other are low. The odds of us hitting each other in the right way are even lower. And the odds of us hitting in the right way with enough energy are even lower. Right? Now, let's imagine all of us are blindfolded. And you have to find me. There's a lot of you now. The odds of you finding me go up dramatically, right? Because there's more of you. Yes?
Yes.
The odds of you hitting me in the right way go up because there's more of you. Yes? Make sense? Now let's imagine there's 50 of me and 1,000 of you. We're going to find each other pretty darn quick, aren't we? Right? That's called concentration. The more of something you have in a reaction, the faster it should react because the chances of that happening go up. Make sense? Yeah. It's just odds. The odds of hitting. So that's why when they spill a bunch of chemical in Europe, say they spill a bunch of reactive chemical into the air in Europe, it doesn't react with chemicals over here. Right? Because they're just not going to find each other. The chemicals over there are going to react with chemicals that are in the air in Europe. Make sense? Just because they can find each other over there. Okay? Alright. That's fun, right? Chemistry's fun. Seriously, right? Alright. Write this word down. Exothermic. Now, I am going to draw a graph, which everyone hates graphs, I know. This is reaction progress. So the reaction is going forward. This is energy. So the energy goes up, reaction goes forward. So we're going to start here. These are our reactants. Reactants. Okay. So the reactant started at a certain energy. We're not going to say what the energy is, it just started at a certain energy. And now, we're going to get a curve that looks like this. And I'll describe what this curve means. And these are products over here. So right here, on this curve, when the energy is increasing here, so as the reaction goes forward, the energy increases to here. This right here are molecules, literally, hitting each other on the upslope. They're smacking into each other. And as they smack into each other, they might increase in energy a little bit, but come right back down. So they increase a little bit, come right back down. Increase a little bit, come right back down. After a while, they'll keep doing that, and the energy will keep increasing. Okay? And to make this go even faster, you could add some heat yourself, right? But the molecules are smacking into each other and going up the energy curve. So they're going up in energy. Except, I envisioned that happening. Anyway. Don't cry or spill water. Okay, so the energy goes up. The molecules collide, the energy goes up. Until they get right here. And then, once they get right here, they cascade down this way. So now, the molecules are smacking into each other. Here, new products are being made. Okay? So the energy comes cascading down. This energy difference between here and there, that's called the energy of activation, or some people call it activation energy. Okay? Activation energy. Activation energy is the energy required to make a reaction go. If you don't have enough energy to get to the activation energy, the reaction will never go forward. So we all know, because we all watch TV, we all watch, police dramas, right? When somebody dies, they take them to the morgue, right? And in the morgue, they throw them in a freezer, right? Why do we throw dead bodies in a freezer? So they won't decompose, right? Well, the decomposition will slow down. Now, when you cool something down, like water, which were made of water, mostly, when you cool water down, the molecules stop moving as fast, right? Molecules in liquid water are moving pretty fast. You cool them down, they move slower, right? If you cool a molecule down so it's moving slower, first of all, the odds of them hitting each other go down because they're moving slower. Right? First thing, they're moving slower. Also, you're taking away heat, energy. So the chances of it getting to the activation energy go down. When you cool something down, the chances of it going to the activation energy go down. So you're probably not going to get to the activation energy. So therefore, you're not going to react. Okay? Does that make a little bit of sense?
Yeah.
So you take a dead thing, you cool it down, it's not going to react and spoil. Or, in the case of a human, decompose. Okay? Because even a decomposition has to get to the activation energy. You with me so far? Alright? So that's why we cool down our food, and that's why we cool down dead humans and dead pets before we bury them. Because we have to keep the activation energy down, prevent the molecules from hitting each other so they don't decompose. Is that okay? Alright. So now, we come down, we cascade down to products. Now notice, the energy here is higher than the energy there. Okay? So we started out here with more energy than the products gave us. Alright? So what happens to that energy? It what? Well, the energy of the reaction goes, of the whole system goes down. But where did the excess energy go?
Released as heat.
Released as heat. Right? So we have gasoline, right? You burn gas in your car. Your car uses some of the energy to move the car forward, but a lot of it's released as heat. Okay? So now you have a molecule, it's reacted, and heat has left the molecule. Okay? Now, read that sign behind you. Look at the sign behind you that said exit, right? E-X-I-T, right? Exit. What's exit mean? Leave. Get out. That way. To leave, you go that way. Exothermic. The suffix, or the prefix, excuse me, exo means to leave, right? EX, leave, or outside. Thermic, heat. Exothermic, heat leaves, or leaves heat. Make sense? So in this reaction, the products have more energy than the reactants have more energy than the starting material. So in this reaction is exothermic. Which means heat leaves. I don't want to say heat leaves, say heat exits. That's better. There. So, There, help you remember. Heat exits the reaction. Okay? So now, when you're doing a reaction that's exothermic, to you, the reaction gets hot. You grab onto it, it burns you. It's hot. Okay? But now, let's think about it from another point of view. You are the chemicals. From the human being standpoint, the reaction is getting hot. Heat is leaving the reaction. From the chemicals' point of view, they're actually getting colder because they're giving off their energy. Right? Does that make sense?
Yeah.
So we see it as a warming up. They see it as a cooling down because they're giving off their energy. Right? It's like when you go up from the outside of Florida, you're hot, you're sweaty, energy is pumping off your body. You go inside the air conditioner and your energy is still pumping off your body. So you're giving off heat, heat is leaving you, but your body is cooling down. Right? Because you're giving off your heat. Make sense?
Yeah.
Say maybe you have a fever. If you have a fever, your body heats up, you're exuding heat, but your body is cooling down. Right? Because you're giving off your energy. Make sense? A little bit? Alright, so let's exothermic. There's another kind of reaction. Endothermic. Endothermic. Same idea, reaction in progress. On the bottom, energy. Over here. Now, here we have the starting materials, or reactants. And the products are up here. Activation energy is here. So from the starting materials or reactants to up here, the very top of the hump, that's your activation energy. Now here, the starting material is at a lower energy than the products. The products are a higher energy thing. So now when you have this kind of situation where energy has to go into the reaction, the opposite of exit is enter, right? Exit means to leave, enter means to come in, right? Everybody?
Yes.
So enter means to come in, so this reaction is endothermic. Heat enters. Endothermic. Heat enters. Exothermic, heat leaves. Now, this reaction, the observer, the reaction is getting cold. The flash will literally get cold. But from the reaction's point of view, they're warming up because they're taking in the heat. They're absorbing it to make chemical bonds. Now, the example of that I can think of right offhand, there's cold compresses for athletes. When you take that thing, they break it, and it gets instantly cold, and they put it against your ankle or whatnot. That's an endothermic reaction. The reaction is taking in heat from you, hopefully. So hopefully your ankle won't swell too bad. So that's an endothermic reaction. Heat is entering that reaction from the surroundings and maybe even from you. Make sense? Okay?
I have a question. So
Yeah.
what happened in the microwave?
So that's a whole different thing. The microwaves are making the water molecules vibrate inside the food, as far as I know.
It's friction.
And it's friction from the water. Yeah. It's a very, it's a complicated process for a very simple device now. See, I can remember back when my family got our first microwave. I remember the day. Seriously, like, you guys all think it's ubiquitous, right? It's everyone's got a microwave. It was a big deal to get a microwave, man. I bet your parents had made it or something, man. You got a microwave, man. We got microwave
Do you
donuts
remember your
now.
first television?
I remember our first color TV, yeah. Color TVs were very expensive when I was young. Now they're, you can buy a huge giant screen TV for less than my father paid for our first color TV. With remote control. Man, we were styling. I'm telling you, man. We had 2 channels and a color TV. Awesome. Yeah, back in the day. Yeah, back in the day we had to use the airwaves to get TV channels too. None of this cable stuff. And the internet, what was that? Yeah, rabbit ears. You know? Everyone's like, rabbit ears? What are you even talking about? You guys know, right? You know. Who else? You might know. There you go. There. Back in the day. Poor people had to do these things. I remember our first VCR. A VCR is a video cassette player. You don't even know what that is, do you?
I had one of those for years.
Yeah, but back before streaming, we had to actually go out and rent the videos from the store. It had Beta and VHS competing for each other. Yeah, Beta. Remember Beta, everyone? Beta?
No, I have no idea.
Thanks for making me feel extra old today. All right. Reaction rate. Rate of reaction. Now, some reactions, you guys already know, go very, very fast. Some reactions go very, very slow. And that's called the rate. The speed at which the reactions are used, or another way of saying it, is the speed at which the products are made. That's your reaction rate. So, for example, a slow process is iron rusting. It's a slow process. Take a piece of iron, put it out on your porch. It won't rust for, maybe a month. You might even get a month before it'll start to rust. You may only get a couple of days. So that's kind of a slow process. Now, a fast reaction would be in your body. That's a great example. Energy production in your body. Why is it a sprinter can get on his mark or her mark, and when the gun goes off, they're accelerating like a leopard down the track? It's a very fast chemical reaction. It happens instantaneously. Zoom, you're gone. When you cook an egg, it's a very fast chemical process. You crack the egg in the hot frying pan, it immediately turns white. It immediately cooks. It's a very fast process. That's reaction rate. Now remember, some things are slow, some things are fast. Now, what will affect the reaction rate? Well, we've already talked about it a little bit. First of all, temperature. If you increase the temperature, molecules will move faster. The rate of reaction should go up. Now take that cadaver or your food, put it in the refrigerator, the rate of reaction slows down because you've cooled it down. Okay, so the molecules aren't moving as fast, not colliding as fast, not getting to the activation energy as quick. Okay? Bottom one, concentration. Remember we talked about how if I was blindfolded and this gentleman was blindfolded, we couldn't find each other. Go ahead.
What about freezer burn?
What about?
Like, what is that?
Let's talk about that. It's not really it's kind of a chemical process, but it's more of a physical process. Increases with concentration. So when this gentleman and I were blindfolded trying to find each other in this dark room, we had a hard time finding each other, so the reaction rate would have been extremely slow. But then throw a million of me and a million of you guys in here, and the reaction all of a sudden goes extremely fast because we can simply find each other. Make sense? So concentration and the heat are the two biggest players when it comes to reaction rate, or how fast you can make a reaction go. Okay? Does that make sense? Concentration and heat. This one, catalysis or catalyst. Write that word down, catalyst. Catalysts are very important in terms of biology, first of all. In terms of our lives, second of all. The catalysts. Catalysts, what they do, in essence, is they make the reaction go faster. But they don't do it by heating things up. What they do is they decrease the activation energy. So remember this energy right here we talked about? We have this energy right here. What the catalyst can do, let's talk about it over here, it's more simple. What the catalyst will do, instead of having to get to this energy, now we could probably get just to down, maybe down here. So the green line is the catalysis. You have a chemical reaction and you throw a catalyst in there, the catalyst will drop the activation energy. Now, what does that do? Well, think of it this way. These are just, we call them energy humps. These are energy humps. The activation energy is what you have to, the hump you have to climb to get to where you want to go. So imagine you're in a park, not in Florida because there's no hills here, but say up north somewhere, and you come across a split in the path. One path goes to this really small little hill, and one goes to that really big hill. Well, which one are you going to be able to walk over faster?
The small one.
The smaller one, right? Which one are you going to pick? The small one, right? As long as they get you to the same place, right? So it's easier and faster to walk over a smaller hump. Does that make sense?
Yeah.
Why? Because it takes less energy to walk over a smaller hump. Same thing as chemistry. Reactants will go over that smaller hump if you give them a catalyst, so they can react faster. Okay? Now catalysts are a lot more complicated than that, but for this class, for now, just accept that a catalyst will lower the activation energy of a reaction. And don't worry about how. Okay? They just do. Make sense? Everybody somewhat happy with that? At least a little bit. And I think that's everything for this chapter. Pretty sure of it, actually. Yep, good. So we're going to start chapter 6. Oh, you thought you were going home early, huh? No, we're too far behind for early days now. Too far behind. I hate when they take away one of my teaching days and they say, well, how come you can't finish your course? Because you took away one of my teaching days. Anyway. Now, in chapter 6, I'm going to go through it rather quickly, and you'll see why when we get there. It's not challenging. It's probably the easiest chapter. There's going to be some math. The math in this chapter compared to other chapters is elementary. You guys will have no problem with it whatsoever. All the formulas I'm going to talk about, I'm also going to give you on exam, so you don't have to memorize them. And I will show you how to use them. Now, I would ask you, I guess I would insist on it, that you read this chapter yourself. I want you to read all the chapters, but if you don't, or are only going to read one, read this one, because I'm not going to go over everything. There's a few things that I want you to go over yourself. The concepts are not hard. They're not hard. Okay? All right. Gases. Gases, gases, gases. You already know a little bit about gases. You know that the molecules of gases are very far apart, and they're moving very fast. We've already learned that. You know that it's easy to walk through a gas because there's a lot of empty space here. Just walk right on through it, no big deal. Right? So, this is what they call the kinetic molecular theory of gas. Gases do not attract each other and they do not repel each other. They kind of do, we say they don't. They're very small volumes, and you increase the temperature, their kinetic energy will increase. So you give them more heat, they'll move faster. That's gas. Okay? And this chapter is all about gases. So far, so good? Just a quick little intro so you can know what we're going to talk about. Now, pressure. Write that down, pressure. Pressure is a measurement of the collisions of a gas particle to the sides of its container. Whoa! Say it again. Pressure is the measurement, or what happens when gas molecules push against the side of a container. So you have your bottle of aerosol hairspray, which I don't even know if they make anymore. Do they make aerosol hairspray anymore?
Yeah.
Oh, they do? I don't have it here. So inside that container is gas. It's pressurized. The little gas molecules inside there are pushing against the sides of the container. That's where the pressure comes from. Your barbecue grill, if you use propane, barbecue grill, the gas inside that container is under pressure. It's pushing against the sides of the container, which is why when you open the valve, the gas will come out, which is kind of convenient, right? But that's what causes pressure, is the energy the molecules are hitting the side of the container with. Which is why if you read the can of aerosol hairspray, it says, do not put in fire. Why? Because if you heat it up, the molecules move faster. And when they move fast enough, they will break the side of the container. The molecules themselves will break it open. Because they're moving fast enough to decrease the structural integrity of the metal. Pretty neat, huh? And you all are thinking, who would ever throw hairspray in a fire? That's because you're all from cities. Now come back to me to the country, where I'm from, and people do that all the time. Not too bright, I guess. It's very dangerous. It can actually fly up and smack you in the face. Volume. I have never done it. So I am in the city now. Volume is the amount of space a gas will occupy. Now you already know that, right? A gas volume is dependent on the container. Gas will take any volume you want. You could take a 5-gallon tank of gas right here. I could open the valve. The 5 gallons of gas will become the same volume of this room. It would. It would just fill the entire room. Now the concentration will go down, but the gas itself will fill the entire room. I could take all the air in this room, if I had the right equipment, I could compress it all down to 1 liter. If I had the right equipment. Okay? So gases will take whatever volume you want. Now, of course, if I take all the air in this room and compress it down to a liter, the pressure is going to go way up, right? Because there's more little molecules per square inch inside the container, right? So the volume goes down, but pressure goes up. All right, so you're good with that so far?
Yes.
All right, you guys are bright. You guys are brilliant people. I love this. Temperature. Now, write this down. Temperature, Kelvin. When we discuss gases, the temperatures must always be written in Kelvin. And I'll explain why in Charles's law. But for now, just write down, temperatures must always be described in Kelvin, not in Celsius. Okay? If you decrease the temperature on a gas, the molecules of gas will move slower. If you increase their temperature, the molecules will move faster. So this is all review, right? We've all heard this before. Except for the Kelvin part. All right? So far, so good, guys? Pressure. Now, don't write this down, just follow along. I'm not going to test you on this stuff. I may ask you what pressure is, and it's the force exerted by the gas on the side of this container. But pressure is measured in force divided by area. So if we have, say, this room has, say, 1 atmosphere of pressure. So there's 1 atmosphere pushing down on this room, or on the sides of this room. Take all this gas, say this room is about, I don't know, 10,000 liters. It's a lot more than that, but let's just say it's 10,000 liters. Compress it down to 1 liter. The pressure in this room now is going to multiply significantly. Why? Because now there's more molecules per square inch pushing on the sides, right? Does that make sense? So the more molecules you have pushing on the sides of the container, the higher the pressure. Should be. Does that make some sense? Yes. Okay. Now, don't write these down. These are in your book, and I will actually give these to you if you need them on the exam. The common pressure units, and the ones that I like to use, are the first ones. Atmosphere and millimeters of mercury. Those are the ones that I like to use. Why? Because I've grown up with them. It's just how it was when I was growing up. Another common one that you see is pounds per square inch. Because most tires are inflated to a standard that's written in pounds per square inch. So you probably are familiar with that one. Pascals is another way. PA, pascals, is another way to measure pressure. In Canada and in Europe, they use pascals a lot. I believe Pascal was a French chemist, some European chemist. In the United States, usually it's millimeters of mercury or inches of mercury, but I don't ever use inches. Or torr. For some reason, they use the word torr. 1 torr is a millimeter of mercury. I don't know why they did that, but they did. Okay? So look for atmospheres and look for millimeters of mercury in this class, because that's what I use. I find it to be the easiest way to do these questions.
So they use those to measure pressure in...
Yep. This is how you measure pressure. 1 atmosphere, or millimeters. All right. Oops. Barometer. Now, pressure is measured with a barometer. Now, where do we get that 760 millimeters is 1 atmosphere? From a barometer. Barometer is basically a pool of mercury right here, an evacuated glass tube right there, and what we've discovered is if you have this pool of mercury and an evacuated tube right here, the atmosphere will push down hard enough on the mercury to raise the level of the mercury by 760 millimeters. It's not very sexy, but that's what it is. That's how we measure it. And we said, okay, here we are at 1 atmosphere, and we have 760 millimeters of mercury. Let's leave it at that. That's how it was born, from a thing called a barometer. Now, have you ever watched the news and the weather, and the weatherman says, there's a low pressure system coming? Yeah?
No.
Watch the weather. Doug, you'll hear it now that I mention it to you. Watch the weather. You'll hear stuff like a low pressure system is on the way or a high pressure system is on the way. You may even hear the weatherman say the barometer is dropping or the barometer is rising. What he's talking about is this. When the pressure, the atmospheric pressure drops, that usually means bad weather's coming. Usually, it doesn't always mean that, but usually that's what it means. A low pressure system is going to rain or snow. High pressure system is like today. Well, kind of like today, sunny, nice. Okay, so the barometric pressure is the atmospheric pressure. The pressure is going up, fair weather ahead. Pressure is going down, storms are coming. Pretty neat, huh? Now you know what the weatherman's talking about. So when you're talking to your friends now, on your way to the clubs, you can say, the pressure's rising. It's going to be nice tomorrow. Atmospheric pressure is the pressure exerted by the atmosphere around us. So we're standing here, the air is pushing down on us, the pressure is pushing on our bodies, so we don't explode. Isn't that nice? Go ahead.
Is there a minimum amount a gas container can be compressed to?
A minimum amount?
Yeah.
Or maximum amount?
A minimum.
A minimum?
Like
Yeah,
you
zero.
have a big gallon.
Yeah, there could be no pressure at all.
Vacuum.
This is called a vacuum. Space.
No, I mean like if there's like a gallon container, is it possible to push it down to like an inch?
Yes, it is possible theoretically, sure. You need to have specialized equipment to do it though.
And I can push it down to even smaller than an inch.
Probably. If you had the right equipment and the wherewithal and the need to do it, you could probably figure out how
So
to
the
do it.
possibilities are endless when it comes to gas.
Well, not any. I mean, once you get to such a small container, the molecules themselves take up space. So you can't compress them any more than the molecules are.
Okay.
So remember, they're really small, but they do have volume and they do have space. So you can compress them down to where all the molecules are touching each other, and that would be called a solid. So you could cool, say, helium down until it becomes a solid, and then it wouldn't be a gas anymore. See what I'm saying?
Yeah.
At a certain pressure, the molecules will solidify.
Oh, okay.
Okay. So yeah, I guess the answer is yes. There is a maximum, because if you compress it too much, they solidify. Neat, huh?
Yeah.
All right. So we're blowing through a lot of this stuff because a lot of this stuff is in the book, and it's this kind of preamble. Now we'll get to Boyle's law. Now I'm going to switch gears down a little bit, slow down just a little bit. Now I'm not going to slow down too much, and you'll see why in a minute because questions aren't hard. Boyle's law. Boyle relates pressure to volume. Now if you're a diver, scuba diver, you worry a lot about Boyle's law. You worry a lot about it. Let's talk about it real quick. Boyle's law says the pressure of a gas is inversely related to its volume. What does that mean? Well, it's inversely related. So if you're inversely related, that means the opposite's going to happen. So if you're inversely related, your temperature goes up, or sorry, not your temperature, your pressure goes up, your volume must go down. Because it's an inverse relationship. One goes up, the other goes down. One goes down, the other goes up. Okay? So imagine that. You have gas in this room at 1 atmosphere of pressure. We shrink it down to half the volume of this room. The volume went down, the pressure went up. Does that make sense? In your scenario, you have a liter or a gallon, you compress it down to a little sphere. So the pressure, so the volume went down, so the pressure went way up, right? Way up. Make sense?
Mm-hmm.
So if you took that same volume, that little cube, and you blew it back up to 3 gallons, the pressure has to go down because the volume increased.
Mm-hmm.
Make sense?
Yeah.
So now, scuba divers think about Boyle's law all the time because you don't want to die. So when you're at the surface, your lungs are filling with 1 atmosphere. Okay? You drop down, the water pressure now is pushing on you. Changes the pressure. So now the pressure's gone up, so the volume in your lungs has gone down. Make sense?
Yeah.
Because the gas molecules are under pressure now, so the volume that you're breathing in is low compared to what you breathe at the surface. So now if you're at like 100 feet, you're taking a big lung full of air, you come up to the surface, you go from being in a very high pressure environment to a low pressure environment. What happens to the gas in your lungs if you don't breathe it out? The gas will expand, right? So you breathe in a bunch of air, say 80, 90 feet down, hold your breath, which you should never do, all the way to the surface. So you're under pressure, the gas is under pressure, you rise up, the gas expands, because that's what gases do when you release pressure. Pressure goes down, volume goes up. If you don't breathe the volume out, your lungs will puncture. And you will feel really bad for about 3 seconds. And then you'll die. I don't know if it's 3 seconds, but I've heard it's very painful. Okay? So that's why scuba divers, when they dive, they breathe out constantly. Because as you change depth, you breathe out, you equalize the pressure again. Boyle's law. As volume goes down, pressure goes up. As pressure goes down, volume increases. Okay? You with me on that?
Yes.
So Boyle's law is written P1 V1 is P2 V2. It's also written pressure initial, or PI. VI is pressure final, PF VF. I don't care how you want to look at it, either way is fine. Okay? So that's what Boyle's law says. Now, if you want to look at the little schematic on the board here, you can look at the piston system on the left. We have 6 little round balls bouncing around inside that little area, at 4 liters, 1 atmosphere. If we push the piston down, giving the molecules half the volume to run around in, they're going to hit the sides of the container twice as often, aren't they? You give them half the room to run, they're going to hit the sides twice as often. Right? Everybody?
Yeah.
On that? So the pressure's going to double, right? So you're going to hit the sides more than double. Okay?
Yep.
So volume goes down, pressure goes
Up.
pressure goes up, volume goes down. Very nice. Okay. So that's the setup. That's how Boyle's law works. Let's try a quick problem. Let me skip to one here. Come on now. Am I going backwards?
Yeah.
There we go. All right. Let's try this calculation together. Now, these questions are dirt easy. It's as easy as getting your house dirty. I promise. Now, Freon 12 is that molecule right there. It's a refrigeration gas. What is the new volume in liters of an 8.0 liter sample of Freon gas, initially at 550 millimeters of mercury, after its pressure is changed to 2,200 millimeters of mercury at constant temperature and N is moles? Okay, so that seems like a hard question. It's got a lot of words. It's got a lot of things being thrown around. First thing you do, read it again slowly and start writing stuff down. Don't get intimidated by these questions, because just take a deep breath. Whenever you see pressure and volume, take a deep breath and say, these questions are easy. Okay, so I read the question again carefully. What is the new volume? So new volume, that's going to be volume final, or volume 2. Volume final is my question mark. And it wants me to say it in liters, so I put the unit right there. What is the new volume, or the last volume, the final one, of an 8 liter sample? So it says, what is the new volume of an 8 liter sample? So my initial volume, where I started with, was 8.0 liters. But feel it? See what I'm doing? Everybody? Okay, so I have VI, I have VF. Now, let's keep reading here. The Freon gas initially, so PI, the first pressure, PI, is 550 millimeters. So PI the first pressure was 550 millimeters of mercury. And the pressure is going to change now to 2,200. So my new pressure, PF, 2,200 millimeters of Hg. Now, the most common question, well, first of all, the most common mistake in these questions is reading the question wrong. People will switch VI and VF, or PI and PF. They'll switch them by mistake. Don't, just read the questions carefully and you can avoid that. The second question is, how do I know whose law to use? Well, you could memorize it. You know, you can say, okay, Boyle's law, pressure goes up, volume, okay, there you go. Or, do it the easy way. Look at the formula sheet. In the formula sheet, there's going to be numerous Boyle's law, Charles's law, Henry's law, all kinds of laws. All you got to do is say, okay, I have a pressure and I have a volume. There's only one law that relates both of those, and that's this one. The other ones will be pressure and temperature, volume and temperature, and molecules and pressure, and molecules and temperature. This is the only one that has pressure and volume. The other ones don't. You get me?
Yeah.
So don't memorize anything. Just go look for that. Just go look for the formula that relates these two things together. Make sense?
Yeah.
All right. So now we're looking for VF. That is what we need, and we know this is our formula. So P1 or PI, VI is PF, VF. This is what we need. So simple, rearrange the formula. That's how I do these questions. I need to get that thing all by itself. So how do I do it? I divide both sides by PF. God bless you. The PFs cancel, yes?
Yes.
Leaving me with a new formula. VF equals PI VI over PF. Okay? Now, before we do any number crunching, before we do any numbers, let's just examine this real quick. So we started at 550 millimeters, and we've what? Is this an increase of the pressure or a decrease? An increase, right? A pretty substantial increase. So our pressure has gone up. So what should our volume do?
Down.
It better go down. So if we do this calculation and our number goes up, we've made a mistake. Okay? So make sure you check your answers for logic. So let's plug the numbers in and see if we get a logical answer. So 550 millimeters of Hg multiplied by VI is 8.0 liters, which is all multiplied by 2200 millimeters. Mercury, units cancel. That's the other thing you should do to check yourself. Make sure the final unit is a unit that you need. If I ask you for the final volume and your unit's in pressure, you've made a mistake. Okay? So what's the number? 2.0?
2.0.
Thank you. 2.0 liters. So, we have the unit that we need. We have a volume unit, which is a good thing. And we've gone from a low pressure to a high pressure, and the volume went down. I have very high confidence in this answer because it's logical and the unit work. Get what I'm doing? Okay, pretty straightforward? All right, let's try another example. You guys can tackle this one on your own. What? A sample of oxygen gas has a volume of 12.0 liters at 600 decimal point millimeters. Now be careful there. 600 decimal point is 3 sig figs. What is the new pressure when the volume changes to 36.0 liters? So we have a pressure and a volume. That's Boyle's law. And I believe he's filling a scuba tank. So try that. Shouldn't take you any more. Well, the first time out, probably take you about 5 or 6 minutes. Once you get good at them, these questions take about 10 seconds. Just rattle them off. V1 and V2. However you want to do it. Anybody got it yet? You people? Who's got it? You folks? Who doesn't have it yet? A couple other people? Are you working forward or are you stuck?
Working forward.
Working forward, okay. Another minute, and we'll have to try a new one. I'm sure you'll get it. Oh, you're calculating it now, so you don't know stuff. It's Friday, by the way. Everyone cheers for Friday. I'm very happy it's Friday because that means tomorrow is Saturday. All right, so let's read the question together. A sample of oxygen gas has a volume of 12.0 liters at 600 millimeters of mercury. What is the new pressure when the volume changes to 36.0 liters? Okay, so the new pressure, this is my question mark, the new pressure. And they want it to be in millimeters of Hg. Now, I'll just tell you something real quick. When I give you a question like this, I will never try to trick you. Now, what I mean by that is sometimes you'll read questions like this, and they'll give you the pressure in one unit and a pressure in a different unit. Like they'll give you pressure in millimeters, and then they'll say, what's the pressure, calculate the pressure in torr after all this other stuff happens. I'm never going to do that, okay? I'm always going to give you millimeters to millimeters, atmospheres to atmospheres, torrs to torrs. I'm never going to ask you to do some kind of weird conversion in the middle. First of all, real life is not like that. Real life is you measure it initially in torr, you use the same barometer, measure it again in torr. You're not going to measure it in inches and then convert it to pascals. That's just silly talk, okay? Nobody does that. So if we're going to be in one unit, we're going to stay in that unit. We're not going to convert out of it. You'll see questions in your book that have you converting inside the question. I didn't write the book, so just kind of roll with it. But in an exam, I'll never try to trick you that way, okay? First of all, because it's not real life. Second of all, it's kind of rude. All right, so a sample of oxygen has a volume of 12 at that pressure. What is the new pressure if the volume changes? So the new volume is 36.0. Oops. Liters. And we have, what do we got now? Okay, the first volume is 12.0. And the initial pressure was 600 decimal point millimeters. All right, so there's our setup. We're relating pressure to volume. We go back to the formula sheet and we see that, okay, only one formula relates pressure to volume. That's Boyle's law. So we know that PI VI equals PF VF. Is that correct?
Yes.
Everybody like it so far?
Yes.
All right. So we're trying to isolate PF. So you divide both sides by VF. So VF will cancel nicely. PI VI divided by VF equals PF. Right? Everybody get the same thing? Actually, let me put that on the right hand side. I'm just going to move the PF to the other side. Alrighty then. PI, 600 decimal point. Now leave the units in. You're tempted, I know you are, and probably half of you or more than half have done it and left the units out. Don't do that. Or do so at your own peril. Liters cancel, leaving us in a unit for pressure, which is a good thing, that's what we want. Now, before we calculate it, let's check for logic. We have volume initial volume is 12 liters. We've gone to 36, so we've gone up. The volume has increased. So the pressure should decrease. Right? Volume goes up, pressure goes down. Pressure goes up, volume goes down. Okay. So here, the pressure should go down. So divide. Multiply 600 by 12.
200.decimal point.
Okay, I believe you. I have my calculator right now. I'm going to do it, right? Yeah, there it is. 200 decimal point. Very good.
If you don't put a decimal point on the exam, will it be wrong?
You get 4 to 5.
Oh, Jesus.
But you have to have the new figures right. The decimal point indicates 3 sig figs. You could also write 2.00 times 10 to the 2. And that would also be correct, but it has to be 3 sig figs. Okay? So be very mindful of that. Watch your sig figs very closely. Okay? Remember in the first day of class I said the difference between an A student and a B student was sig figs?
Yes. Oh my God.
It's true.
Last test,
It's true.
I've seen that.
But the third test, don't let it happen again. And you'll be amazed. You'll just jump up. Okay, so very good. So everyone got that, right?
Yeah.
Everyone kind of understood it? Very nice, very nice, very nice. There's a whole bunch of other questions here. We're just going to jump to the next one. So the ones that I skipped over, the little learning checks, go back and just do them. Make sure you can crank them out. They're not any harder than what we just did. They're actually the same kind of difficulty. Now, temperature and volume. Well, we know that if we heat up a gas, the gas moves faster. So if the gas is moving faster, it could take up more volume, right? It could. Let's just think about that for a minute. Charles's law. If the temperature of a gas is directly related to its volume. If you take a gas and you decrease its temperature, its volume will go down. You all know, well, maybe you haven't seen that because you don't live in the north. Take a balloon, blow it up. Blow the balloon up. Tie it off, throw it in the freezer. Wait an hour. Pull the balloon out. Does anyone know what will happen to the balloon? It'll shrink, it'll shrivel, right? Because the gas inside the balloon has lost energy and the volume has decreased. Does that make sense? So the volume that was pushing out against the balloon now is not there, so the balloon is going to shrivel a little bit. In Florida, what you do is you take the balloon, fill it up, take it outside, and what will happen? It'll pop. Eventually, it'll pop. Why? Because you're putting more energy into the balloon, into the gas. The gas is beating against the sides of the balloon harder and harder and harder until the balloon loses integrity and bursts. Okay? So if you increase the temperature on the gas, the volume will go up. Go ahead.
I have a question. What about if you, because I feel if you put a can of soda and you get it in your car and you heat it, it explodes.
Yep. Well, that's Henry's law. That's a different law. That involves solubility of gas.
Okay.
So that's a different thing we don't talk too much about in this class. But it's true. You heat up a soda can, the gas pressure will, and then you're having a bad day. Okay, so temperature. Heat up a gas, the temperature goes up, cool the gas down. Sorry, heat up a gas, volume goes up, cool the gas down, volume goes down. Now the caveat is pressure and N are constant, where N is moles, or the amount of gas. Okay? So as long as the pressure and the amount of gas stay the same, you increase the temperature, the volume goes up. You decrease the temperature, volume goes down, as long as pressure stays the same and the amount of gas. All right? Now Charles's law is not the same as Boyle's law, but it looks very similar. It looks very similar. Charles says that Ti over Vi equals Tf over Vf. That's what Charles says. Now, notice here, they've written it Vi over Ti, and I wrote it Ti over Vi. Both are correct. So I'll just write down both so you'll see. Vi over Ti equals Vf over Tf. This and that are the same formula, just flipped over. Okay? So don't let that fool you. It's the same formula.
Would it give you different answers?
Nope. Nope. And to prove it to yourself, when you go home tonight, take one of the questions we're going to do here in a minute and work them using both formulas, and you'll see same answer. If you do it right. If you do it right. Okay, so increase the temperature of a gas, the volume will increase. Decrease the temperature of a gas, the volume will decrease. Charles' law. All right, let's do a problem. Always helps to do a problem. A balloon has a volume of 785 milliliters at 21 degrees. If the temperature drops to 0, what is the new volume of this balloon? Ha-ha! Put the old balloon in the freezer trick. That's what this is. So, we don't know what formula to use. We're on an exam. We're kind of freaking out because, we want to get an A and we're doing so well in the class. We don't want to get this question wrong, so what do? Well, we read it carefully and pull out the pertinent information and leave the other stuff behind. A balloon has a volume of 785 milliliters. So VI is 785 milliliters. That's V. TI equals 21 degrees Celsius. All right? All right, we'll throw it in the freezer. Okay, TF. TF is 0 degrees Celsius. VF. Okay, that's what we don't know. Okay, we don't know VF. And that has to be in milliliters, right? Is that what it wants? It doesn't say. So we can pick whatever volume unit we want. I choose milliliters. Why? Because our first volume is expressed in milliliters. Don't make the question any harder than it has to be. Okay, so here we have 21 degrees Celsius. Now we have to convert that to Kelvin, but I haven't told you why yet. So let's work this question without converting it to Kelvin, and you'll see immediately why we have to convert to Kelvin. Okay? So let's do this question real quick. TI over VI equals TF over VF. Okay, so let's just start putting our numbers in right away. So we're going to get 21 degrees Celsius over VI 785 equals TF is 0 over VF. 0? Wait a minute, what? If we follow this to its conclusion, we're going to get 0 as an answer. Well, we know darn well, if you put a balloon in a freezer, it doesn't disappear. Right? So this can't be right. Using Celsius can't work. Right? Because if you use Celsius, you're half likely to get a 0, or worse, a negative volume. A negative volume is called, I guess, a vacuum. So that can't work. So you must convert to Kelvin. Why? Because Kelvin never goes to 0. Unless you're at absolute 0, which is impossible to accomplish. Okay? So that's why you have to convert to Kelvin, so that your volumes won't become 0 or negative. Everyone like that? Yes. Is that a good explanation? Because I just made that up. I'm just kidding. I'm just kidding. So let's get rid of this. This offends me. This offends the eye. Let's get rid of that. Now the first thing we're going to do when we're on an exam and we're given a gas question and there's a temperature, we're going to convert that temperatures, or both temperatures, to Kelvin. Why? Because it's the first thing we have to do, and you'll get 1 point or 2 out of 5 or 10. So you get something for doing it. All right, so what is the conversion for Kelvin?
Add 273.
Very good. Add 273. So now it's going to become 294. Right? Okay, so we converted both temperatures to Kelvin. Easy, no problem. Here we go. Okay, now we need VF. And we know that these formulas are true. Let's use this one. Why? Because it puts what we need in the numerator. It makes our life easier. Okay? So VF, so multiply both sides by TF, right? So the TFs cancel, which leaves VF equals TF VI over TI. Is that true? Multiply both sides by VF. True, right?
Yes.
I hope. Tell me if I'm wrong. So let's take this formula. I'm just going to move it to here because it gives me more room to play. VF equals TF VI over TI. Plug in my numbers. TF, this is right here, 273 Kelvin, multiplied by VI, which is 785 milliliters. All of that now divides by TI, which is 294 Kelvin. Before we crunch that number, let's do a logic check. Let's be logical first. So we're going to go from 21 degrees to 0. So my volume should do what? Should
Yes.
get less. Decrease. Anything else? Everybody.
Decrease.
One more. Hello, everyone. Say it. The volume should go down because the temperature went down. So if my number here is bigger than my number there, I've made a mistake. Also, make sure the units will cancel, leaving you in a volume unit, milliliters. Okay? Do all of these things to check yourself to make sure you're right. And you don't want to be wrong, especially on easy questions like this. These are like 3 points on an exam. Let's crank it out now. 273 multiplied by 785. All of that is divided by 294 equals. I get 729.
I have 727.
Okay. What did everyone else get? 729? So my balloon will shrivel up just a little bit. Okay? Everyone happy with that?
Yes.
Is that much different than Boyle's law? Not really. The process is kind of the same, right? Just a different formula. Right? So these are like 3 points on an exam, right?
Yes.
Kind of, yeah. Yeah, what?
Did you round it?
Yes. All right. Good job, guys. Try this one. Oh, go back. Go back. Go back. Okay, cool. Try that one. Now, be mindful of this question. A sample of oxygen gas has a volume of 420 milliliters at a temperature of 18 degrees Celsius. At what temperature in degrees Celsius? So you're going to convert everything to Kelvin, get a final answer, and convert out of Kelvin into Celsius. Okay? Be mindful of that kind of stuff in an exam. Don't get that wrong. That's the point right there. And don't forget to check the logic of your answer. How we doing, guys? Rocking and rolling, get it done? Who's got it done? You folks? Okay, keep working. We've got the calculators in hand, so they're just about done. Now, I want to give you a piece of advice. These questions are easy. There's no doubt about it. They're easier than anything we've seen so far in terms of math. But what you want to do is practice them so that you get, bang, 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 quick. Because say this is a 10-point question on an exam out of 100. If you can knock out 10 points in less than 5 minutes, you've taken a huge step forward in terms of advantage. Now you have extra time to do the multiple choice, which is by far the most time-consuming part of the exam. Don't take these for granted. Because if you get to an exam and you haven't practiced it, you're going to be really slow at it. You want to be quick. Because this is an easy, I think everyone will agree these questions are easy, or easier than the normal questions. These will be on your exam. You can knock them out, man, you're moving forward quick. And that's what you need to do. Okay? It's also a good strategy to learn how to take tests. Because if you're going into nursing or any kind of allied health, you're going to be taking a lot of tests. Strategy is part of the game. How did everyone do? Everyone get it? Raise your hand. You got it. Put your hands in the air. Wave like you just don't. No? Nobody? Oh, there we go. One person. There we go. Thank you. Thank you. You're the only excited person I have, so I talk to you the most. All right. So, what's the answer going to be? B, 170? Everybody agree? Let's crank it up together, and we'll move on. One more thing, and then we're out of here for the day. All right, let me write this question up. Now, I like Boyle's law, and I like Charles's law's questions, because I think they're the most relevant. There's one more law we're going to learn that's also fairly relevant. You can ask Siri, but she won't help you. Now, sample of oxygen gas has a volume of 420 milliliters. So let's write that in, 420. Now what else we got there? And the temperature is 18 degrees Celsius. The final temperature is, we don't know, and the volume will be 640. This is my question mark in degrees Celsius. Okay, so add 273 to that, and what did you get?
291.
Thank you. Kelvin. This one we still don't know. So TF is my big question. So multiply both sides by VF. That will become VF, oops, sorry, not VF. TF equals VF TI, all divided by VI. That's my formula, or my rearranged expression. TF equals VF TI, all divided by VI. Plug in some numbers now. 640, oops, milliliters. Multiply that by TI, which is 291. Divide that now by VI, which is 420 milliliters. And you got, what did you get in Kelvin?
443.
443 Kelvin. Okay. Before we do anything, let's do a quick logic check. Temperature went up, and my volume went up. So that's good then, right? Temperature goes up, volume went up. So this is logical. The units work too. So I feel confident this is right. Convert it to degrees Celsius, minus 273. And I get, what was it, 140? 170. Put a square on your final answer to make grading easier for me. The happier I am when I grade, the better the marks are. You know, like everybody, I'm a human like everybody else. The happier I am, the more generous I am. So if you make me work, it's not as good. All right, so let's get to one more thing and then we're out of here. Gay-Lussac's law. Gay-Lussac's law. Now you're going to see here in a minute, Gay-Lussac's law looks just like Charles's law, but it's slightly different because it relates temperature to pressure, not volume. But the way we work the questions are the same. All right? So don't get intimidated by Gay-Lussac. It's exactly the same as Charles's law, except for now it's pressure, not volume. If we leave the volume of a container the same and we heat up the gas, the volume can't change because now we're in a rigid container. So the pressure is going to go up if you increase the temperature. If we decrease the temperature, the pressure will go down. But the volume won't change because we've made it a rigid container. Okay? Does that make sense?
Can you say that again?
If you increase the temperature on a gas and the volume can't change, so you're using a can, for example, a hairspray can. If you increase the temperature, the pressure of the gas in the can will go up. But the volume can't change because the can won't expand. It will explode, but it won't expand. If we decrease the temperature of the gas in that can, the pressure will go down, right? So pressure and temperature are directly related. And the formula for Gay-Lussac's law is not TIVI, it's PI-TI. Gay-Lussac's law. I just usually abbreviate it GL law. PI over TI equals PF over TF. Okay? That's Gay-Lussac's law. That'll be on your formula sheet as well. So when you're working a question, don't know which formula to use, go back to the problem and read the question carefully, figure out what's related to what, and you'll figure it out. Let's do a quick example and call it a weekend. Oops. A gas has a pressure of 2 atmospheres at 18 degrees Celsius. What is the new pressure when the temperature is 62 degrees Celsius? All right, that's a typical Gay-Lussac's question. Now, like every other problem I've shown you how to do today, pull out the information that is pertinent and ignore the rest. Let's just erase all this stuff and start here. So, a gas has a pressure of 2.0 atmospheres, so PI equals 2.0 ATM. What else we got? Oh, TI, 18 degrees Celsius. What else we got? What is the new pressure? P2 or PF? Question mark. But what's the unit going to be? Doesn't say, so we'll use atmospheres. Haha, make it easy on ourselves. TF equals 62 degrees. First thing I would do, convert both my temperatures to Kelvin. What's that going to be? 912, anyone?
Yes. 335.
Oh, thank you. All right, so we have that expression. So we need to have PF. Looking just like Charles's law, doesn't it? So we need this one. So we're going to multiply both sides by TF. So PF equals TF PI over TI. That's what that expression is going to look like. So I'll come over here just to solve the whole question. PF equals TF PI over TI. Now, TF, where is it? There it is. 335 Kelvin multiplied by PI is 2.0 atmospheres. All of that is divided by TI, which is 291. Kelvin, cancel, leaving me in an atmosphere, which is a pressure unit. So that's good. My units are making sense. Now, we're going from 291 to 335. So we're increasing the temperature. So therefore the pressure should
Increase.
Very good. So if my number comes out to be smaller than 2, I've made a mistake. 335 multiplied by 2 divided by 291 is?
2.3.
2.3 is good. 2.4 or 2.3?
2.3.
Good enough for me. That's the answer. Now does that look just like Charles's law?
Yay.
Alright. Now, that's it for me in chapter 6. However, you are responsible for the entire chapter, so please read it. It doesn't get any harder than this. But read the whole chapter. Make sure you can do the combined gas law questions too.